Hi, in this video we're going to go over an example on linear impact loading. This is example 7.1. The example reads as follows. A 6-ton elevator is descending at a constant velocity of 300 feet per minute when the mechanical lift system binds and the elevator stops abruptly. The elevator is suspended on a 2-inch diameter steel wire rope with approximate modulus of elasticity of 11.7 times 10 to the 6 psi. We're going to assume that the wire rope is 80 feet long when the accident happens, and we're going to estimate the maximum elongation and maximum tensile stress in the wire rope. Now before we solve it, let's go ahead and go over the general procedures for solving linear impact problems. The very first thing that you're going to do is to calculate the static deflection. What is the static deflection? In all of the impact problems, you're going to see a mass or a weight striking an object. So let's say, for example, you have some column and a mass is going to strike it, right? This mass is moving down. Maybe we know the height from which it's dropping, or maybe we know the velocity at which it's traveling when it strikes the objects, right? Regardless of which of the two quantities are given, the mass is going to strike the object, right? We need to calculate the impact factor, and one of the most important things that are in the impact factor equation is the static deflection. So what is the static deflection? Static deflection is, forget that mass is striking the object, right? And instead we just set it up on top and we calculate how much this distance here, let's say this is the original, and that's how much this distance here, which is how much does the object being struck is gonna deflect if we just put this mass over here and we let it rest, right, and achieve static equilibrium, right? So that's the very first thing we want to calculate, the static deflection, right? The important thing, why we want it, because we're going to need it for the impact factor. Now we have two equations for the impact factor. One of the equations is going to depend on h, and the other equation is going to depend on v. Let me change color so you can see it better, right? Regardless of which equation we're using, the static deflection is going to appear in the two equations, right? So we have that one. The next question is, which of the two equations we use? Well, the question we want to ask ourselves is, what information do we know, right? What is happening? Do we have the case where a mass or an object is traveling with a known velocity? If so, we use the second equation, right? If they don't tell us a velocity, if instead they tell us, hey, a mass is just free falling, right? It's just free falling with acceleration of the gravity, right? They're going to tell us from the problem statement how height is going to drop from, right? So we can determine the final velocity. And once they do that, we're going to know that we have to use this first equation over here. So again, the impact factor, all you have to do is read the problem statement and say, okay, what is it that I know? The velocity at which the object is traveling, or we just know the object is free falling and we know from what height. Once you have the impact factor, we're going to go ahead and calculate the maximum deflection and the maximum, and the equivalent force. To calculate those is super easy. Once you have your impact factor from above, you're going to multiply that impact factor times the static deflection, the two numbers that you calculated in the previous two steps. And those two combined or multiplied by each other is going to give us delta, which is the maximum deflection, right? What is this maximum deflection? Is a combination of the two. So how much deflection we would have gotten from just the static, right, from the mass just sitting and static loading, plus a multiplier, right, this impact factor, which is capturing the dynamic effect. Anyways, that's for the maximum deflection. Next, we will also calculate the equivalent force. So this is just the weight of the object that is striking, right? And also we're just going to multiply it times an impact factor, right? This is going to tell the structure that it feels X amounts higher, right? Where X is from the impact factor, that's a multiplier. So when we're looking with a linear problem, whenever we have something loaded, linear means along its long axis, right? So if we want to calculate, for example, the maximum stress developed, we know that the equation for stress is just force per area. In this case, we're going to use the equivalent force, right? Which is just a magnified or a blown up number of the initial, of the weight of the mass striking the object, again, times the impact factor. So let's go ahead and try to solve this problem. I'm going to start by writing what we know, or our knowns. We know that the elevator weighs 6 tons. So the weight of the elevator is 6 tons. And we want that in pound force, right? Every ton is 2,000 pounds. So 6 times 2 is 12,000 pound force. It is descending at a constant velocity. So V equals 300 feet per minute when it stops. The elevator is suspended on a 2-inch diameter steel wire rope. So the diameter of the wire rope is 2 inches. With approximate modulus of elasticity of 11.7 times 10 to the 6 psi. Here a little note on approximate modulus of elasticity. If you ever looked at a wire rope, you'll see that if we look at a cross section, for example, of a wire rope, it's not one solid piece of metal. Instead, it's a bunch of steel cables, right, that are packaged together, right? So all of these together are gonna have, it's gonna behave also linear elastic, right? There's gonna be some flex to that cable, and they measure it. This is from the material, well, from the wire rope suppliers you can look into. And depending on the configuration of how this wire rope is created, the strands, and how it's actually weaved or wrapped together, you're going to end up with different stiffnesses, right? So you'll get those from, again, from the vendor. These guys are saying that this wire rope has approximate modulus of elasticity of 11.7 times 10 to the 6. Now they give us the length of the rope as 80 feet. So that length is going to be this guy over here. So this drawing is obviously not to scale, right? But this is 80 feet. And now we want, so this is our knowns, and we want to know max elongation and max tensile stress. So the very first thing we want to do, if you go back to the general procedure, right, is just calculate the static deflection. Here, what are we calculating the static deflection of? Well, they're asking about elongation and tensile stress on the wire rope. So we want to calculate the static deflection on that wire rope. So although this wire rope, if we look at the cross section, right, it looks something like this. So do you remember how to calculate deflection of something that is maybe cylindrical like looking and it's very long, right? Hopefully you remember that to calculate that deflection is going to be, it's an axial deflection, so we're going to use the play equation, PL by AE. So let's go ahead and plug in the values. P is going to be the weight of the elevator. Again, what we're doing is we're asking the question, how much would the rope sag or deflect if the elevator is just hanging on it, right, and it's already in static equilibrium. So that's what we're trying to solve. So this P is 12,000 lbf. The length is 80 feet. There's an area over here at the bottom, which usually the area is in inches. So let me go ahead and convert the 80 feet to inches, right, by just multiplying by 12. Next is the area. They tell us the diameter is 2 inches, so the area is going to be pi by 4 times 2 squared. Remember, that is in inches. Next is elastic modulus, which in this case we're going to use the approximate modulus of elasticity. So this is times 11.6 times 10 to the 6 pounds per square inch. Now I didn't write the units of this one, but this is in inches squared, and this over here is in pounds per square inch, right? So these is going to cancel with this, and the pounds are going to cancel with that, and we're going to get the deflection in inches. So we plug all of this in the calculator. 12,000 times 80 times 12 divided by pi by 4 times 2 squared times 11.6 e to the 6. I get 0.31611. So that is the static deflection. Next, what we want to do is, once we know the static deflection, we want to calculate the impact factor. Remember, there's two equations. One is in terms of h, a drop height, and the other one is in terms of velocity. And so here's the question is, which one are we going to use, right? And sometimes you might get a little confused because here we have an elevator, right? And they give us this length over here, which you might confuse as a height of 80. So you might guess, look, oh, I want to use the one with the height, but that's not a correct answer, right? That h would be like a free fall height. That would be the equivalent if I drop the elevator, like if it were to bungee jump, and that elevator falls 80 feet before before the cable is all like tight and it bounces back up, right? So that's not the one. Instead, we know that it's traveling at 300 feet per minute. It's a constant velocity, so it's coming down at that speed. So we know the v. So next, we'll go ahead and calculate the impact factor. So the equation for impact factor is going to be 1 plus the square root of 1 plus, again, since we know the velocity, it's v squared divided by gravity times the static deflection, close parentheses. So here we go. So we put our number 1 here plus square root of 1 plus the velocity is 300 feet per minute. That quantity is going to get squared, but let's check the units before we square it. Why do I say that? Because at the bottom we have gravity, and gravity in US customary units is 32.2 feet per second squared. Right on the top we have a velocity of 300 feet per minute. So probably we want to convert this one to seconds so that we have the same units, right? So we know that in 1 minute there are 60 seconds. There we go. So we can again square this quantity because it's velocity squared. So at the bottom we have the gravity, and then this gets multiplied times the static deflection. the static deflection was 0.31611 inches. But again, when we're looking at the units, I see, oopsie, hold on. Come on. I'm trying to use the highlighter and it's not letting me. There we go. The units is feet. We have the static deflection in inches, so let's go ahead and convert this to feet now, or foot. Can never say it properly. So we know 1 foot, there are 12 inches. So let me go ahead and make all of this. So this is what we're typing in the calculator. So here we go. 1 plus the square root of 1 plus 300 divided by 60. That quantity squared divided by 32.2 times 0.31611 divided by 12. Now when I do this, I get a impact factor of 6.52. Let me just make sure I plug in the right answers in my calculator. 1 plus 1, 2 divided by 60, 0.31611 divided by 12. Yeah. So that's our impact factor, right? This is telling us how much we're gonna magnify both the elongation delta and the tensile stress. So now when we go back to the question and figuring out the maximum elongation, once we have the impact factor, we know that that maximum elongation or delta is gonna be the static deflection times the impact factor. So in this case, the static deflection was 0.31611 inches. And this is going to get multiplied times 6.52 times. Remember, the impact factor is just a number. So just to double make sure, let me go through the units, right? So I got foot up on top is going to cancel with this one. Minutes cancels with this one from the conversion. Then second squared is going to cancel with that one. What else? Remember this, foot up on top, it gets squared. So I have feet squared on top. So one cancels here. The other one is this other one. And the inches were canceled from the unit conversion. So at the end of the day, the impact factor should be unitless. Good point, I remember that. Okay, so we have the delta. So I'm going to take 6.52 times 0.31611, plug in the calculator, and we're getting a value of delta equals 2.061 inches. So that would be max deflection. Next thing we need to calculate is the maximum stress. Okay, we already kind of hinted that we're looking at this wire rope like a very long cylinder, right? We know the axial stress on a cylinder is P by A. In this case, the equation that we're going to use, right? What is the load? The load is not the weight of the elevator. It's the weight of the elevator times the impact factor. So remember this formula over here. The equivalent force is going to be the weight times the impact factor, which is 12,000 pounds times 6.52. So if we take 12,000 times 6.52, this gives 78,240 pounds. This number here is the equivalent force. This is what the wire rope is feeling from the dynamic effect, from the abrupt stopping, right, because it had an initial velocity. This is very good estimate as to what the cable is feeling, right? So the stress is then going to be the equivalent force divided by the cross-sectional area. Again, we're going to take this value and stick it over here. So we have 78,240 divided by the cross-sectional area. Remember, this wire rope had a diameter of 2 inches squared, right? So when we take 78,240 and 78,240 divided by pi by 4 times 2 squared, this gives roughly 24,904. Let me round up, 905. And the units are pounds per square inch. So PSI, this is the stress maximum. And over here was the maximum deflection. There we go. Now, just for fun, let's see what would happen if we pick the wrong equation for the impact factor. So if you remember, we have two equations. One depends on the velocity given. The other one depends on the height, right? So what is the one with the height? Let me erase a little bit. The one with the height, if we have used that one and said, well, I can claim that the elevator, right, has dropped a height of 80 feet. And that would not be entirely correct for this discussion of the impact factor. Because what that would be is, let's assume we have the wire rope, right? It's all untangled and we have the elevator. And then we just let it like free fall until all the wire rope is stretched and you have something like this, kind of like a bungee jump. That would be to the equivalent of using the impact factor with H instead of the velocity, so a completely free fall. So just for fun, let's calculate what that impact factor would be if we had been using the wrong one again. So the impact factor for H is, the formula is almost the same thing. It's 1 plus square root of 1 plus twice the height divided by the static deflection. So let's go ahead and put the values. 1 plus square root of 1 plus 2 times the height, so 2 times 80, and the height is in feet. So let me go ahead and multiply it times 12 so that we have it in inches. That way I can take the static deflection, which is already in inches, and stick it in here. 0.31611. There we go. So if we type this on the calculator, we have 1 plus square root of 1 plus 2 times 80 times 12 divided by 0.31611. So now look at the big difference. I'm going to color this one magenta because this is the wrong one, but that would give an impact factor of 78.9. Look at the big difference between the two. Again, this one that we calculated initially, the elevator it's descending, right? So it's on its way down, but it's at a constant and controlled velocity, and then something jams up on top and you feel that jolt. Maybe you felt that in the elevator down at the engineering building. It's happened to me a couple times, right? That's what that impact factor was. If we use the other one, if we use the other equation, which is this guy, right? This is the equivalent of the elevator free falls for 80 feet. right? And then we run out of wire rope, it stretches and you get that big old jolt. So that big difference, right, because of the velocity that it's going to acquire, is going to feel 78 times more than its initial weight. So imagine, for example, the stress over here, right? You're going to take, for example, 78.9 times the weight of the elevator, right, which was 12,000 pounds, and then all of that gets divided by the same cross section, which is pi divided by 4 times 2 squared. So if I type that, so if I figure out that stress, which would be again 12,000 times 78.9 divided by that area, my calculator tells me that the stress would be 301,375 psi. So much higher than the value that we had observed. See, 24,000 psi, it's okay, it's reasonable. The elevator, the cable would handle that, but 301,000 psi, probably not. Anyways, it's a fun exercise I like to do when I teach in front of the class. Just what are the implications of this from using the impact factor. Again, just want to remind you here, the correct impact factor is 6.52 because the elevator is traveling with a constant velocity. It's not free falling from an 80-foot drop. So hopefully you enjoyed the example. If you have any questions or if you picked up on any mistakes, do let me know in the comments down below. Otherwise, we'll see you on the next one.